Okay, so structural induction, bird's eye view. Okay. Think of inheritance and ancestry and how traits pass from one generation to the next, and in that sort of process is the essence of structural induction. Okay, so let me illustrate. Orks. Okay. Just some fictitious character. Okay. And I'm going to tell you that, so orks, just like humans, they mate, the pairs of them mate, and they have children, and, this whole process continues generation after generation, and you get, you started with 2 orks, so you started with 2 orks, and then this happens for centuries and millennia, and now you have, 4 billion orks. Okay. So, what I'm going to tell you this. Okay, you started with 2 orks, and they both had blue eyes. Okay, good. Now I'm going to tell you something else. Okay, I'm going to tell you that, when 2 orks mate to have a child, okay, and, now, there may be, different mating rituals and whatnot, and, I'm not making any sort of restrictions on which 2 orks mate, but what I'm going to tell you is that when 2 orks mate to have a child, if they both have blue eyes, the child will have blue eyes. So if 2 orks mate to have a child, if both have blue eyes, then the child has blue eyes. Okay, so in other words, this is a trait that is passed down from parents to children. If both parents have this property, blue eyes, so in words, okay, so think of, you have ork 1 and ork 2 who are about to mate. Okay. And if ork 1 has blue eyes, and so ork 1 and ork 2 mate and produce, ork 3, which I could write maybe as little O3 for a baby ork 3. Okay. So if O1 has blue eyes and O2 has blue eyes, so O1 and O2 have this property. Okay. If these two hold, then O3, the little baby ork created, O3 has blue eyes. Okay, so, imagine that we have, we have recursively defined this set of orks, which starts with the primordial ancestors, these first 2 orks, and then, you have your constructor rule, which is that if any 2 orks come together, they can mate and produce a child. Okay, so that's a way of getting new orks into my set. Okay, and now I have a property of orks, which is called blue eyes. And if 2 orks mate and they both have blue eyes, which, if 2 orks mating is part of the constructor rule, so if 2 orks who mate to produce a child and if they both have blue eyes, the child has blue eyes, okay, then the question we're going to ask is, what can we say about all the 4 billion orks today? Okay, in particular, do all the 4 billion orks today have blue eyes? Okay. What can we say about all the 4 billion orks today? Okay, and intuitively you can sort of convince yourself that, well, this is just inheritance, right? If a trait is passed, without any change, 100% accurately, if a trait is passed from parents to children, then all the children will have that trait. Okay, providing that the parents have that trait. And then the children of those children will have that trait. In other words, when could a green-eyed ork have popped up? So, when could a green-eyed ork have popped up? Because the primordial ancestors had blue eyes. And so if a green-eyed ork popped up somewhere down the road, well, you can consider the first green-eyed ork that popped up and ask, well, if that's the first green-eyed ork that popped up, well, then the parents were blue-eyed. Because that's the only way to create a new Ork. And if the parents were blue-eyed, then how did this green-eyed Ork pop up? It's not allowed. You're violating the rules of inheritance. Okay. And so this sort of intuition of inheritance and, how traits are passed from one generation to another is the essence of structural induction. Okay. So let me summarize structural induction. Structural induction. Induction. Okay. So here's the basic idea. You show that your primordial ancestors have some property. In this case, blue-eyed. And in this case, I didn't show it. I just told you. That's a fact. It's true. You can't argue with a fact that I tell you. It's true. I tell you it's true. It's true. Okay. So you show that the primordial ancestors have some property P. Okay. You just show it. Okay. And then you must show, if you can show, that this property P, this trait, this property P is passed from parents to children. So this property P, the property P is passed from parents to children. Okay? If you can show that the primordial ancestors have this property, the first two Orks, and if you can show that whenever parents get together to produce a child, the property is inherited without flaw. Okay? Then the principle of structural induction says that you can conclude that all of your, population, the entire population, conclude that the entire population has the property P. Okay. Now, we could prove the principle of structural induction. It's just a straightforward application of strong induction. We could prove it from the well-ordering principle. There are many ways to prove it, but I'm going to, rely on your intuition to take this as, it makes sense, and you can see the text, in chapter 8, gives a much more thorough discussion of how we would, go about proving this. Okay, but instead, let me just show you how does this apply to recursive sets. Okay, recursively defined sets. Well, who are the primordial ancestors? Those are your base cases. Okay, so the equivalent of the primordial ancestors are the base cases in a recursively defined set. So these are the base cases. Base cases. Okay, and what is this, this concept of a property? Well, that's a predicate. So you make a claim. So the input will be a member of your set, okay, an element of your set. That's the domain of the predicate. And the predicate says makes some claim about that input, that element of the set. For example, has blue eyes or is even. Okay, so this property P, that's what we call a predicate. Okay, and now what's this notion of from parents to children and so on and so forth? Well, we have to go back to the way in which a recursive set is defined. Okay, and and there are base cases, and then there's a constructor rule. Okay, so in a recursive set, there's a constructor rule. Okay, and what does a constructor rule do? It says that if some object is in your set, X is in your set, let's say set, then Y is in your set. Well, there's no reason to limit constructor rules to just being able to construct new elements from one element. Okay, so we can generalize the constructor rule. So in the example with the set A, one element produces another element, but you could have multiple elements like a pair of Orks, i.e. the parents. So you can have multiple elements, constructing or producing, a new element. So we could have a constructor rule like, if X and Y are in your set, then, X plus Y is in your set. Perfectly valid constructor rule. Okay, and in general, what we say is that on the left-hand side are the parents, and on the right-hand side are the progeny or the children. Okay, makes sense. These guys got together and produced via the constructor rule these guys. So that's the notion of parents and children. And what we're saying is that if the property P holds for the parents, okay, then it holds for the child created. What that means is that the constructor rule preserves the property P. Okay, and important, it's an if-then. It doesn't have to produce children with the property P unless all the parents have the property P. So providing that all the parents have the property P, the constructor rule has to preserve the property P. Okay, and then the principle of structural induction comes and tells you, bam, your whole set has the property P. Okay, so you have to prove it. You have to prove the property P for the base cases, and then you have to prove that the constructor preserves the property P. And now we're going to do lots of examples of this. Okay, starting with the set A. Okay, so let me erase. You know, the super duper speed erase. Okay, so, you know, the formal justification of structural induction is through strong induction. And you can read all about that in the text. Our goal is to do loads and loads of examples so that you get comfortable with the mechanics of structural induction. So we'll illustrate in many different, you know, settings. Now, you know, the intuition is, you know, probably enough to justify structural induction at this point, which is that, you know, this notion of inheritance and how traits are passed. If the primordial ancestors have some property and procreation preserves that property, the word preserves is important, preserves that property, okay, then the whole population has that property. So let's start with this set A. Remember, we defined this set A, you know, so it's a recursive definition. So 0 is in A, and the constructor, if X is in A, then X plus 4 is in A. Okay, so what is A? It's 0, 4, 8, 12, 16, and so on. Okay, so we want to show, now we're going to use structural induction to show that everything in A is even. So everything in A is even. Okay, and there are two steps. The first thing is you must show that the primordial ancestor, the very first, you know, elements in A have this property. In other words, the base cases have this property. So that's the base case of your structural induction. And so we need to go to the base cases of the recursive definition, and there's only just 0. So we need to show that, you know, even is a property of the base case, so the primordial ancestor, and 0 is even. And that's clearly true, so check. So we've shown the base case. We've shown that the primordial ancestors of this recursive set satisfy my property, which is evenness. Now, okay, so this is the induction step. Okay, show that the way you get new objects, so the procreation process, preserves the property. Show that procreation preserves the evenness property. Okay, now how do we show that the procreation process preserves it? So it means that, you know, so you have to look at the constructor rule, okay, and, you know, you look at the constructor rule and preserves means that if you started with that property remains, okay. So we have to show that for the constructor, okay, if you start with the property, then the property is preserved in the offspring. Then the property is preserved in the child. Okay, so if you start with the property, i.e., you know, the parent has the property, then it's preserved in the child. So let's see. So we have to, in the constructor rule, we have X that is in A, okay, implies X plus 4 is in A. So X is the parent, Okay, and the new object that's created is x plus 4. So this is the child. So we have to show that if the parent has the property, which is even, if x is even, then x, the child, has that property. X plus 4 is even. Okay? And to prove this, we can use a variety of methods. Let's just use a direct proof. If x is even, so x equals 2k, that implies that x plus 4 equals 2k plus 4, which is equal to twice k plus 2, which is twice a multiple, which is twice an integer. So this is even. So that means that x plus 4 is even. And so this evenness property is preserved by the constructor. So evenness is preserved. And so by induction, okay, every element of A is even. Is even. End of proof. And now, even though technically this is structural induction, we still say by induction because induction is induction. All inductions are equivalent. Okay, and if we want to sort of justify structural induction, we do it through strong induction. So this is it's essentially the case that structural induction is strong induction in disguise. Okay, so it is induction. Okay, now let me emphasize. Okay, so here are the mechanics. You have to prove the base case. So you have to prove that your property, whatever you're trying to prove for every element of A, you have to prove that the base case satisfies that property, and then you have to prove that the constructors preserve the property. Preserve means that if you start with parents that have that property, so all the parents must have that property. So if you start with parents that have the property, then it must be the case that the child has that property. So the parent produces a child. If the parent has the property, the child has the property. Okay, now let's look at that other question quickly, just to be complete. Okay, so is every even number in A? The answer is no. For example, 2 is not in A. Okay, and let's ask another question, which is true. Is every non-negative multiple of 4 in A? Is every non-negative multiple of 4 in A? Okay, and the answer is yes. Okay, and in fact you can prove that A equals the set of all non-negative multiples of 4. So we proved that every element of A is even. So now I encourage you to use structural induction to prove that every element of A is a multiple of 4. Okay, so prove that every element of A is a multiple of 4. And now I'm going to do the reverse question. Is every multiple of 4 in A? Just to illustrate how we answer that second question. Okay. So the answer is yes. And now what's the proof? Okay, the proof is by contradiction. Okay, so suppose it's not the case. Suppose not. Then by the well-ordering principle, there's some smallest multiple of 4 that's not in A. By well-ordering, there is some smallest multiple of A, some smallest multiple of 4 not in A. So let's call that smallest multiple of 4 x star. Okay, x star is not 0 because 0 is in A. So x star is greater than 0. Okay, so that means that x star is greater or equal to 4. And it's a multiple of 4. Okay, that's not in A. Okay. Then let's consider x star minus 4. Well, this is greater or equal to 0. Okay. And x star minus 4 is a multiple of 4 because x star is a multiple of 4. So this is 4k minus 1. So this is 4 times k minus 1. Okay, so this is a multiple of 4. Okay. And therefore, x star minus 4 is in A. Now this is the important, conclusion. Okay. So it's a multiple of 4. Okay. Now why do we know that it's in A? Okay. Because it's greater than or equal to 0, so it's a non-negative multiple of 4, and it's smaller than x star, so it must be in A. Why? Because x star is the smallest one that's not in A. So by the well-ordering principle, this guy is the smallest, and since this guy is strictly smaller, that means that this must be in A, because x star is the smallest multiple of A of 4 not in A. So this is a multiple of 4. This is a multiple of 4. It's smaller than x star. Therefore, it must be in A, because otherwise x star wouldn't be the smallest guy that's not in A. Okay. So this means that x star minus 4 is in A. So x star minus 4 is in A. But then the constructor says that x star minus 4 plus 4 by the constructor, x star minus 4 plus 4 is in A. But this is just x star. And that's a contradiction, because we just saw that x star is the smallest guy not in A. How can it be that x star is the smallest guy not in A, but then it's also in A? That's fishy. Fishy. Okay. And therefore, suppose not was false. That means that every multiple of 4 is in A. End of proof. Okay. That's just to show you how we answer the other kind of question. It's a much more complicated question to answer. It's usually a proof by contradiction, where you say, okay, let's consider this, all things, of the kind you're interested in. In this case, multiples of 4. Well, if, they're not all in there, then there's some smallest guy who's not in there. Then you work around, you explore, and get a contradiction. Okay, good. Okay, so let's do another example.